Estamos en vivo.
Buenas noches, estimados socios. Bienvenidos a una charla más de nuestra Asociación Mexicana de Geofísicos de Exploración en el ámbito de geofísica en hidrocarburos. Esta noche tendremos la presentación del doctor Lev Vernik, denominada Rock Physics. A continuación, el doctor Vernik se presentará y continuará con su charla. Dr. Lev, go ahead, please, and welcome.
Can you hear me okay?
Yeah, we need some echo. Maybe there's a microphone open there.
Okay, so
Go ahead, please.
my name is Lev Vernik. I will be presenting rock physics modeling for carbonates. The reason we have a problem with carbon, that's not possible.
You hear some very far away and some echo in your microphone.
Because because I wanted to present in my iMac computer, and iMac somehow your system doesn't take.
Federico, ¿puedes apoyar con los ajustes ahí?
Say it again.
Try again, Dr. Lev.
Okay, let me start my presentation. Even though it's kind of strange, the echo is very, very significant. And I'm not sure I can be totally understood here. I apologize for any inconvenience, but this is a technical glitch. I had a presentation on iMac system, but iMac system somehow in Mexicana, the Geofísicos de Exploración doesn't like it. So I'll try to do my best, but I guess we're stuck with this stuff.
Hey, Lev.
Yeah.
If you want, you can share the presentation with me so I can show it and you just speak. So maybe you don't have the echo because you can work directly in your iMac.
How can I share it?
So you can stop sharing if you want.
Okay, so I don't know what can I offer at this moment. It's quite impossible to speak here because there is an echo, and I barely hear myself. As I said, my presentation was designed for Apple computer presentation, but your system does not allow the Apple computer presentations or doesn't allow the Apple displays. So I really don't know what else can I say.
Now we hear you better, but I don't know if you still hear the echo. We hear you better, but I don't know if you still hear the echo. So if you want, send the presentation to me so I can show it.
Let me turn my other computer totally off and we'll start.
Okay. Excellent.
Can you see the screen?
Perfect.
Can you see the screen?
Yeah, and we hear you well.
Okay. So my name is Lev Vernik. I'm sorry for the delay. There was a problem here with the computers, but I'm ready to start. I have about 35 minutes presentation dedicated to rock physics modeling of carbonates. My esteemed colleague, Dr. Alan Moore, was a co-worker on this project, and we presented our study last year at SCG conference in Houston. So the agenda of the presentation is as follows. We'll first discuss some modeling rock physics background. Then we'll consider some applications of rock physics modeling in carbonates, followed by the introduction of the Vernik-Kachanov model to calibrate the world carbonate data set that we assembled. Then we'll discuss some modeling studies of interest, specifically scenarios in Middle East and pre-salt Brazil, and finally draw some conclusions. The rock physics modeling background, basically we published a paper a couple of years ago where we discussed what are the benefits of doing rock physics in general in geophysical applications. Rock physics 30 years ago was very immature science, but today is much more mature, much more accurate, and much more useful. But the question's still there. So one of them, can the model, the rock physics model, be calibrated using easily acquired data and observations? Can the calibrated rock physics model be readily used to identify and predict damaged and missing data in petrophysical logs, for instance? Is information about petrophysical properties of interest a product of the calibration process? Is the RPM useful for forward and reverse modeling? So we focus on the effects of mineralogy, porosity, pore shapes, and the effective stress on elastic properties of limestones and dolomites in a wide range of porosities from 2% all the way to 45%. So the challenges in rock physics modeling today are basically related to three different situations. Situation number one is relatively greater stiffness implied by the carbonate mineralogy. So the carbonates are made largely of calcite and dolomite, and those are stiffer minerals than quartz, clays, feldspars, etc. Number two, more advanced diagenetical cementation happens in carbonates as compared to sandstones. So the amount of cement could be exceeding 50%. And then finally, complex pore microstructures than this. For instance, this is a grain pack of spheres with interspherical pore space. This, a dual porosity implementation in Castor and Toxus, shoe pane, or Bakel. So the dual porosity is made up of ellipsoidal, perfect ellipsoidal inclusions with varying aspect ratios. Fat and thin. Finally, compliant pore space, where you can implement some kind of stress dependence using exponential functional form, which is displayed right here. So the challenges with this implementations are as follows. In carbonates, we basically rarely see structures such as this, unless we are talking about suspensions on the ocean floor of some oils of carbonate pellets. The problem with the dual porosity DEM presentation of ellipsoidal inclusions in a solid matrix is that this type of pores are basically not seen by geologists in carbonate rocks. So these are highly idealized pore structures that barely bear any resemblance on real carbonates. And then finally, this, the compliant pore space presentation is useful for stress modeling, but it's quite cumbersome and not quite useful for porosity modeling. So we decided to use the Vernik model that was originally introduced about 10, 11 years ago, and it was used for sandstones. But the consolidated version of this model can be easily applied to carbonates. Even more so, it's probably more useful in carbonates than in sandstones, which was originally designed for sandstones. So the mathematical code for the model is as this. So the KD is a dry bulk modulus, and GD is a dry shear modulus. And the form of this expression is such that we have three terms. Term number one is the matrix bulk modulus, or minimal matrix. Term number two is the contribution of the pore space through porosity, and then term number three is the contribution of effective stress and crack density parameters, which is right here. So the microcracks and pores will have added compliance to the solid composed of the minimal matrix. The same applies to shear modulus. So more specifically, pore shape factors, considering calcite coat material. If we are talking about spherical pores, the expressions for pore shape factors are readily available in terms of the matrix Poisson ratio. However, the pores are not necessarily always spherical, as in some old, like 20, 30 years old rock physics models were considered. We might have triangular or hypercycloidal pores in 2D. You know, of course, you can imagine what this type of pore would look like in 3D. That would basically be a tetrahedron, and this would be a sphere. So the pore shape factors grow, increase, as soon as the pore shapes start to deviate from the sphere. And so the triangle will be softer than the sphere, more compliant. That's why the pore shape factors for P and Q, respectively for bulk and shear modulus, are greater than the spherical pore shape factors. And then finally, hypercycloidal pore shape factors are greater than the triangle. The contribution of cracks is considered through ellipsoidal inclusions of aspect ratio less than 100. And the stress effect implemented through the exponential form, which is shown right here. Interesting fact here is that we have pretty good idea about the mineral moduli of all the minerals that make up carbonate rocks, such as calcite, dolomite, and etc. Anhydrite. Stevensite specifically is of interest. Is the clay, quite unusually soft clay that is found in pre-salt carbonates in offshore Brazil. And of course, we know the fluid properties as well. brine, oil, and gas, and this can be changed according to our needs. So it's good to see the mathematical form of this model, but it's much better to see how it's expressed visually. So here I'm going to show you 3 plots sequentially. In the first presentation, it shows the dry bulk modules as modeled as a function of porosity in carbonate, in limestone, with different pore shapes. So if you assume that all the pore space in limestone is spherical, with change in porosity, we predict the change in modulus according to this trend right here. And the pore shape factor of 2.5, as you already have seen. This type pore shape factor of spheres. Then we go to triangular force, and then we go to hyperboreal force. And we can go further. We can complicate the shape very significantly. The most important element is that the more concave the pore shape is, the more compliant it is, the greater the pore shape factor is. So in this left side, I keep the crack density constant and the stress constant. And so the only parameter in the model that I change is the pore shape factor. Here in the middle, I keep the pore shape factor constant at 7.5. So that's this lower case in this block. And then I keep my stress constant as well. Of course, this is a vertical effective stress. And the only parameter that I change here is the crack density parameter. So on the top, this curve right here reflects the low crack density of 5%, and the lower curve, a much more significant crack density, which is still on the moderate side. The difference between these two representations is that, as you can see, that the model suggests that the effect of pore shape factors will lead to line divergence with porosity. The higher the porosity, the bigger the difference between the effects of micromechanics in pore space. But if you keep the pore shapes the same and just change the crack density, then you see, instead of divergence, a convergence with porosity increase. And that means with high porosity, it's really less significant effect that we observe from crack density as compared to low porosity. So the effect of cracks is very significant at low porosities from 0 to about 10%. And finally, we can show the implementations of the model when we keep the pore shape factor constant, we keep the crack density constant, and by the way, the crack density at 0 effective stress defines the stress sensitivity of the model for your specific role. And so you can see that 50 megapascal effective stress line on the top and 10 megapascal on the right. So you can see that this model is pretty diverse and pretty comprehensive, and all the scenarios of micromechanics can be handled in one or two equations. A significant element that is missing in sandstone environment is the complexity in pore shapes in carbonates. So when you're talking about carbonates, you can see all kinds of different pore geometries, and it's virtually impossible to prescribe any kind of simple geometrical shape to specific shapes that we observe lithographically or in scanning electron microscopy observed in carbonate. So one trick here is to use what Robert Zimmerman suggested, and he introduced a so-called geometry factor, which would be a function of the perimeter of any specific pore and its area. So if you know the perimeter and you know the area for each specific pore using image analysis, you can compute the geometry factor. Well, guess what? The geometry factor, when multiplied by the pore shape factor of the spherical pore, gives you the actual pore shape. which is basically a compliance. In a bulk module sense, it's a compressibility, but in a shear sense, it's a shear compliance. But before I do that, let me show you how we can extend this model from consolidated domain, which is shown here in blue, with velocity from 0 to about, I would say, 27%, maybe 30%, into unconsolidated or poorly consolidated velocity domain. So the poorly consolidated velocity domain in sandstone is very well developed, and the majority of very shallow oil and gas reservoirs in relatively clean sands, such as carbonates, really belong to this phase of poorly consolidated elasticity. And then finally, we reach a critical velocity beyond which we don't have a rock anymore. It's a suspension, and we know how to handle the elasticity of the suspension. It's pretty much a Roy's averaging or wood flow. But in order to handle this tricky transition zone, we introduce these two functions here. So the significant element of each of these functions, this is a P-wave modulus for dry rock, and this is a shear wave modulus, of course, is this dependence on the modulus of the consolidated rock at the porosity, which we call the consolidation porosity. So that's a transition period between the consolidated and poorly consolidated porosity. So this consolidation porosity, in addition to critical porosity, is also dependent, just like critical porosity, it's also dependent on grain sorting characteristics of any specific rock. And of course, the N and M exponents are parameters that can be easily calibrated. They pretty tightly distributed around P. So now let me introduce the data set that we compiled for the purposes of our model calibration. We basically looked at everything published over the last 35 years, beginning from the publications of Rapavich, Arco, then Eberle, University of Miami, Veiko, same place, Fabricius in Denmark, and finally Guilherme Vasquez published a very nice paper on pre-salt carbonates in Brazil. So this data set here, which is basically color-coded by facies or the location sometimes, because some of the facies, like for example the Brazilian clean limestones, they are not really similar to anything. They have significant amount of quartz and sometimes a speed inside, so they are quite unusually colored. So we decided to separate them as separate facies. But other than that, we show typical carbonate facies, such as carbonate mudstones, shown in purple, wacky stones, shown in cyan, packstones in blue, and then grainstones. The best carbonate reservoirs are typically grainstones. They're shown in light brown color here. Finally, the dolomites are separated into red color, or maybe dark red sometimes. You can see. And also we see a sticking out of some of this dark green data points or active data points. They belong to Stevenside Ridge limestone, also from pre-salt Brazil. And this type of displays, like density versus velocity, shear wave velocity versus P-wave velocity, and then acoustic impedance versus porosity, are typical rock physics cross plots that rock physicists worldwide utilize to learn more about the rocks and how to use them. Geophysical applications such as AVO modeling and inversion. So now let us put it all together. So here we show this data set that we have already discussed, the entire data set without any exceptions, separated by facies, or sometimes locations, and then we superimpose them with the Vernik model extending over the consolidated domain with the consolidation porosity of about 30% here, and then seamlessly continuing to unconsolidated or fully consolidated domain, ending somewhere around 60% porosity, which we believe is might be considered a pretty good idea about critical porosity of chalks. These are the images that we actually analyzed, and we showed that this specific limestone here, with this type of pores and certain porosity, has a pore shape factor ranging from 3.8 for P or for P waves to 2.9 for shear waves. They are visibly close to each other, and they are slightly greater than or more compressible than spheres. Of course, we see that they are deviating from the spheres. There might be much more crooked pore shapes, such as, for example, this. These are not pores that can be described by any kind of aspect ratio, because there are some popular models that kind of operate with aspect ratios and include these models. But there are some pores that really don't lend themselves for aspect ratio analysis, because for instance, a equilateral triangle and a sphere will have about the same aspect ratio, but vastly different compliance characteristics. So we can see that we pretty nicely match the three entities here: the dolomites, with of course different matrix characteristics, the limestone. Interestingly, that limestones with different faces and different textures pretty much plot very tightly in acoustic impedance versus porosity space. And then finally we have outliers, such as very soft Stevensite rich limestones from pre-salt Brazil. Both acoustic and shear impedance shown here, and we see pretty much consistent situation in both situations. Now, the VK model, as we refer to, also allows you to model the stress dependence of your rock. That is very significant in 4D application, or even in exploration when you are trying to extend the depth of exploration without having any logs, without having a nearby well bore where you can calibrate your model. And so this stress dependence here is hidden in the crack density curve. So why is that the case? Well, imagine that you have micro cracks that would be very low aspect ratio, and they would be stress sensitive. Under certain stresses, they will close. They will tend to gradually close. And this gradual closure of micro cracks leads to nonlinearity at relatively low to intermediate effective stresses. And then finally, you reach the plateau where the velocities would not change dramatically anymore. So again, this same model, without any specific calibration, can be used for stress sensitivity analysis as well. So, rock physics model summary. We can say that this model demonstrates specific advantages over the ellipsoidal inclusion-based methods, which are still popular, and there are lots of presentations that use Custer and Cox's and Shu and Pei modeling. Well, here I show basically this is a VP-VS ratio versus acoustic impedance. And the color coding here is that we saturate the dry moduli with gas, then we have pink data points, then with oil, green data points. And we don't show the water-saturated limestones other than how the model prediction looks like. And then we show the Stevensite-rich carbonates right here. So you can see that at very high impedances, even at medium to high impedances, it will be very difficult to separate using seismic inversion the oil-saturated from gas-saturated carbonate rocks. So we can before. And that can be dealt with if you know how to do the density inversion. Of course, that is a challenge by itself. But that's a different presentation. So the advantages of the model, we can list them here. That the true pore geometries may be evaluated through 2D analysis, and that opens the possibility of cross-property mapping, for example, permeability or reducible water saturation from elasticity. The significant advantage is that realistic pore shapes can be imaged using petrographic techniques, and the shape factors distributions can be evaluated using image analysis. And then, of course, straightforwardly, fluid substitution is straightforward without any concern for ambiguities related to, for example, dual porosity situation like in inclusion model. An example of that is actually shown here. Another confirmation of what I mentioned about the sensitivity of tight carbonates to fluids, it can be visualized on this plot, which is my favorite in fact, acoustic versus shear impedance. So all of this limestones and carbonates and dolomites are brine saturated here, and the dotted line is a dry limestone line. And you can see that only at relatively low impedances or high porosities, like in chalks, like in Denmark, for instance, you can stand a very good chance of using ABO and seismic inversion, simultaneous two-step inversion, to separate the gas versus brine versus oil in pipe. So that leads us to believe that this is the model of choice, and we wanted to use that to build a specific load scenarios and then explore them using Zoe's equation P reflectivity, which we basically convolve with zero phase SEG standard polarity wavelet, shown here. The spectrum of this wavelet is roughly displayed right here. And then we, by means of blocking model, which is built using the EK model for different scenarios, like this is anhydride, we inserted a grainstone reservoir of different porosities. And then on the base, it's underlined by the carbonate mudstone, very tight carbonate mudstone with 5% porosity. So we vary porosity from 10% to 25% in this specific displays of ABO synthetics. And we model wet responses, which is here and here, versus oil responses, which is track number 2 and 4. So you can see that various scenarios of porosity and fluid saturation can be very successfully modeled using this approach. And what we observe here in this scenario, which is typical of the Middle East, is we mostly see a class 4 ABO responses on both top and base interface of the carbonate reservoir. But the strength of these responses varies quite dramatically depending on whether or not you have an oil reservoir or you have a wet reservoir, or if you have an even low porosity reservoir, relatively low porosity, 10%, you still can stand a chance of amplitude inversion in terms of the reservoir properties to see the difference between the wet or water-saturated carbonate from oil-saturated carbonate. A different set of scenarios can be built in pre-salt Brazil. That's what we've done recently. And in this case, we use 15% porosity limestone and dolomite reservoirs in the middle, and they are overlain by a salt layer on the top and a shale or Stevensite Ridge limestone or marl on the base. So the diversity of AVO responses is much more dramatic here, as you can imagine. So for instance, if you have 80% calcite, 20% dolomite, oil-saturated reservoir, you see a significant reflectivity, class 4 at the top, transitioning from the salt, and then at the transition from the good reservoir to the marl, the shale, you see an opposite polarity, class 4 response. So this would be a class 1, this would be a class 4. Again, the class 1 plus maybe class 2P response with a positive transition with a change in the polarity across the spectrum of angles from 0 to 40 degrees. Now, finally, we arrive at together that is modeling 80% calcite, 20% clay reservoir, poor quality reservoir, and still is 50% oil. And you can see that there is a significant difference between this type of response and this type of response, or this type of response. So the conclusion here is that in each specific case, a geophysicist must do the modeling, and he must do the modeling presumably has good logs. If he doesn't have good logs, then I would encourage him to use a to use raw physics models, such as I presented. And then you can relate the synthetic AVO signatures to the actual gather, CDP gather, amplitudes in the field, and then make a definitive conclusion. So to conclude my presentation, I would say that we have compiled a high-quality database of dry laboratory measurements on a variety of carbonate rocks with diversity of textures and mineralogical composition, and also coming from different stress situations in the subsurface. We have calibrated the DK model and demonstrated its impressive performance over the entire porosity range represented. We used this globally calibrated model to produce a series of AVO synthetics and synthetic gathers, which reveal distinct relationships between the seismic and petrophysical properties. So this exploration of petrophysical properties or petrophysical relationships displayed in logs, when convolved with seismic wavelet to produce the seismic display, is probably the most challenging and interesting part of any specific geophysicist work task. And then finally, the resulting elastic properties of petrophysical perturbations are more likely to be accurate, thus exploration and development objectives can be better realized. So, in other words, the better your model is calibrated, the more accurate it is, and it can be used in the forward modeling sense to fill in the gaps, the missing portions of the log, or even restore the log if it's bad acquisition or any kind of problem whatsoever. So I will thank you, and I'd like to show the references here, because this is the presentation that we published in SEG abstracts, and the paper is probably coming pretty soon in geophysics, so stay tuned. Thank you very much.
Thank you very much. ¿Hay alguna pregunta? Is there any question? Miguel?
If there's no question, that may mean two things. Everything is clear, or nothing is clear.
I think it's hard to understand at the first time. We need to digest.
Have an opportunity to digest.
Yeah, I think so. Miguel, ¿no hay ninguna pregunta? Okay, there's no questions. That can be good or can be bad.
That's what I said.
Well, if there's no questions, we are going to go to grant a recognition to Dr. Lev Vernik. Si no hay preguntas, vamos a pasar a dar el reconocimiento al doctor Lev Vernik. Me permitiré leerlo. Dice: la Asociación Mexicana de Geofísicos de Exploración otorga el presente reconocimiento al doctor Lev Vernik por su brillante conferencia Rock Physics of Carbonates. Well, Doctor, it's a very nice presentation. I think it could be very useful because our main reservoirs here in Mexico are in carbonates, and some of them in natural fracture carbonates. Then I think the natural fractures introduce another variable. And my personal question is, how do we handle that?
You're talking about the effects of microcracks and fractures on velocities in carbonates, right?
Sorry, I couldn't hear you.
Can you hear me now?
Yeah.
Can you hear me now?
Yes, I can.
So my understanding is that the question was, how do we model the effects of cracks in carbonates, right?
Yeah.
Okay. Well, the model that I showed you specifically knows how to deal with cracks, because it has a specific parameter right here. The third term of the model is actually the crack density term. It's a little bit more involved here because we allow the crack density to be stress dependent. But in general, this term right here, this fraction, is the crack density parameter. So when it's multiplied by the specific coefficient, which is a known function of the Poisson ratio, that gives the additional compliance contribution due to cracks or fractures. And that would, of course, lead to a reduction in the bulk and shear modulus and respective reduction in P and S-wave velocity.
This is obvious considering open fractures, not cemented.
Not
assuming
necessarily.
that.
The fracture, if the fracture is fully cemented, then you don't have a fracture. So if you have a fracture, it might have some asperities which might be cemented, and that will lead to a reduction in compressibility. And you will have to modify the crack density parameter, which is kind of an interesting thing by itself. But in general, as far as I'm concerned, this model is the best model to handle fractures, because the models of the exclusion type, like here, like for instance, if you consider that to be a fracture, well, that is not a fracture, because the aspect ratio here might be something like 1/10, maybe 500, and it's not stress sensitive. So the effect of aspect ratio in this range of like less than 0.1 and more than 100, the effect of velocity on velocity in dry rock will be negligible. So it really, the aspect ratio is not a parameter that is useful in rock physics modeling, other than in static applications of stress, because the fractures tend to close the stress. But if the fracture is of that aspect ratio, it won't close at stresses typical in subsurface reservoirs that we deal with. And much higher stress will be needed to close this type of fracture or even this type of fracture.
Okay. Okay, I think I got it. Thank you very much. Well, there's no more questions. I appreciate your time to share with us.
Gerardo,
See?
it's a couple of questions in YouTube. So if you want, I can share with you.
Okay, please say to the doctor the questions. Thank
The
you.
first one, it's about if you can share your experience working in these lab experiments and well, I think it's not complete the question, but it's related to share your experience working in these lab experiments.
Okay, well, I don't have any lab experience in carbonates. What we've done recently with my colleague Alan Moore from Ikon Science is we applied the same type of tool, the model that we developed with Mark Kachano from Tufts University some 10 years ago. We applied it to carbonates, and it's very useful in carbonates as well. So we just compiled a data set measured by some other people. And this data set seems to be pretty comprehensive. It covers a significant range of velocities and porosities in rock microstructure, in mineral composition, and porosity. And we applied our model to this data set pretty successfully, calibrating the model. And so we believe that this is the way to go if you want to learn something about the rock and apply forward modeling to compute logs from rock physics. We prefer that, at least in Ikon Science, and I know other people use it too.
Okay. The second question is, what is the implication of the anisotropy?
The implications of the anisotropy are significant if you have a unique fracture set with significant preferred orientation of fracture planes. If you have a situation like that, the fracture-induced anisotropy might be significant, but nothing in comparison to shales or even especially organic shales, where the anisotropy values are typically greater than 20%, sometimes greater than 30%. In carbonates, even if you have a single fracture set with a huge preferred orientation, you may be thinking about no more than 5–7% P wave anisotropy, which is very often in seismic applications, especially onshore, is very difficult to deal with. If you, in a more typical situation, superimpose one fracture set by another fracture set, which is what I observed in the field, for instance, then you basically cancel the anisotropy and you're dealing with back to isotropic rock with fractures. And our model, the Vernik model, is designed for isotropy. But of course, the modification of this model can be also used in shale reservoirs, organic shale reservoirs, as I show in my book, with significant anisotropy. But in carbonates, I wouldn't worry about anisotropy at all.
Okay, thank you. And the last one is how to take in account a combination of cracks and bugs.
Cracks and what?
And bugs. I don't know what it's.
Bugs?
Yep.
You mean, what kind of bugs are we talking about? Pores?
I don't know because I don't make a question.
Yeah, well, we know that some organic carbonates are made out of skeletons of some microorganisms. So
I think it's a bugular porosity.
So the the bugs, VUG, the bugs, not bugs. I'm sorry.
Yeah.
Bugs. All right, so bugs, of course, will be a significant effect on elasticity if you know your pore system. So, for instance, this type of pore system is buggy porosity. So the bugs are mostly more or less rigid pores, and at the same porosity, they will typically show higher modulus, and at the same porosity, higher modulus, other than compared to some more crooked pore shapes and compliant pore shapes. So that is definitely a significant effect. Well, this display here in the middle shows the crack effect. And you can see that the crack effect is different in the dynamics of change as a function of porosity. So the cracks will pretty much reduce their significance with increasing porosity, while the pore shape factors will increase their significance for elasticity and velocity with increasing porosity. So that's a principal difference between the pores of different shapes and different densities of microcracks and cracks in the solid matter. Does it make sense?
Yeah. I was thinking about this is I think is the last question to close the presentation. I'm thinking, how can we take this in account to predict in an exploration sense? For example, when we are trying to predict a good quality of reservoir rock, we do an isotropy analysis and try to predict the density of fracture and the orientation of it.
Right.
Then when we use this approach, we make a model based on our data we have close to the area we're going to explore. And then we can predict with this is my thinking. We will be able to predict what kind of porosity is working on that reservoir rock. Could be possible?
Yes. It is not unique, as you can imagine, not only in carbonates, but in general in geophysics. But the best way to do it is to do the synthetic modeling using ADO, as I showed in a couple of slides here. So building different scenarios. For instance, if you know from your geologist that works next door to you that the reservoir in the specific area is expected to be a good quality grainstone limestone, but he doesn't know what porosity that would have. Then you know what the overlying rock is. For instance, in this case, anhydrite, and in a lower case, at the base, it's carbonate mudstone, very high carbonate mudstone with very low porosity. So you can build different porosity scenarios and then saturate them with different fluids, oil, gas, water, and then produce synthetic models and compare them with seismic gatherers. And that will dramatically improve your understanding of the possible scenarios. Moreover, you can
play, if you use the Born-Kashana model, for instance, you can play with the crack density and stress. And so on the top of what I've done here, you can change the crack density and then see if that would lead to any significant amplitude variations with offset. So in other words, a geophysicist's role is very, very important always. So you look at the gathers, you do synthetic modeling, you compare the synthetic with your gather, you tie the wells, or you do the predictions using rock physics or modeling, and that will always improve your ability to predict the reservoir quality and reservoir porosity, and even sometimes the heterogeneity, such as different scales of heterogeneity, different porosity variations, different structural variations, and microstructural variations. This is, of course, much more difficult to do, but the simple scenarios such as porosity variation, fluid variation, mineralogy variation, and the pore shape variation, the pore compressibility variation, can be modeled successfully using forward modeling science.
Well, I think it's hard to think about it, but if we don't try, we will never do it. Thank you very much, Lev.
Good, very good. Thank you very much.
Muy bien, buenas noches a todos. Muchas gracias por su atención a esta presentación excelente para que nos quede un sabor de boca. Casi nunca hacemos análisis de ABO en carbonatos porque lo consideramos un caso tabú. Se dice que no hay respuesta que podamos predecir adecuadamente. Sin embargo, con esta presentación nos están demostrando que ya hay maneras de empezar a hacer esto. Thank you very much again, Lev. Gracias, Federico, y gracias a todos por su presencia, y los esperamos en la próxima presentación. Muy amables.
Muchas gracias a ustedes. Saludos.